Now let's look at another behavior of mixture model. And in this case, let's look at their response to the data frequencies. Okay, so what you're seeing now is basically the likelihood function for the two-word document. And we know in this case the solution is to give text a probability of 0.9 and a probability of 0.1. Now, it's interesting to think about a scenario when we start adding more words to the document. So what would happen if we add many this to the document? Now, this will change the game, right? So how? Well, picture what would the likelihood function look like now. Well, let's start with the likelihood function for the two words, right? As we add more words, we know that we have to just multiply the likelihood function by additional terms to account for the additional occurrences of the. Since in this case all the additional terms are the, we're going to just multiply by this term, right? So for the probability of the. And if we have another occurrence of the, we multiply the again by the same term, and so on and so forth until we add as many terms as the number of this that we add to the document, d prime. Now this obviously changes the likelihood function. So what's interesting is now to think about how would they change our solution. So what's the optimal solution now? Now, intuitively, you would know the original solution, 0.9 versus 0.1, will no longer be optimal for this new function, right? But the question is, how should we change it? Well, in general, there's sum to 1. So in order to change it, we must take away some probability mass from one word and add the probability mass to the other word. The question is which word to have a reduced probability and which word to have a larger probability. And in particular, let's think about the probability of the. Should it be increased to be more than 0.1, or should we decrease it to less than 0.1? What do you think? Now, you might want to pause the video a moment to think more about this question, because this has to do with understanding of important behavior of a mixture model, and indeed all the maximum likelihood estimator. Now, if you look at the formula for a moment, then you will see it seems that now the objective function is more influenced by the than text. Before, each contributed one term. So now, as you can imagine, it would make sense to actually assign a smaller probability for text and to make room for a larger probability for the. Why? Because the is repeated many times. If we increase it a little bit, it will have more positive impact. Whereas a slight decrease of text will have a relatively small impact because it occurred just once. Right? So this means there is another behavior that we observe here. That is, high frequency words generally will have high probabilities from all the distributions. And this is no surprise at all, because after all, we are maximizing the likelihood of the data. So all the more a word occurs, then it makes more sense to give such a word a high probability, because the impact will be more on the likelihood function. This is in fact a very general phenomenon of all the maximum likelihood estimator. But in this case, we can see as we see more occurrences of term, it also encourages the unknown distribution theta sub d to assign a somewhat higher probability to this word. Now, it's also interesting to think about the impact of probability of theta sub b, the probability of choosing one of the two component models. Now, we've been so far assuming that each model is equally likely, and that gives us 0.5. But you can again look at this likelihood function and try to picture what would happen if we increase the probability of choosing a background model. Now, you will see these terms for the will have a different form, where the probability of that would be even larger, because the background has a high probability for the word, and the coefficient in front of 0.9, which is now 0.5, would be even larger. When this is larger, the overall result would be larger. And that also makes it less important for theta sub d to increase the probability for the, because it's already very large. So the impact here of increasing the probability of the is somewhat regulated by this coefficient, 0.5. If it's larger on the background, then it becomes less important to increase the value. So this means the behavior here, which is high frequency words tend to get high probabilities, are affected or regularized somewhat by the probability of choosing each component. The more likely a component is being chosen, it's more important to have high values for these frequent words. If you have a very small probability of being chosen, then the incentive is less. So to summarize, we have just discussed the mixture model, and we discussed the estimation problem of mixture model, and in particular we discussed some general behavior of the estimate, and that means we can expect our estimator to capture these intuitions. First, every component model attempts to assign high probabilities to high frequent words in the data, and this is to collaboratively maximize likelihood. Second, different component models tend to bet high probabilities on different words, and this is to avoid a competition or waste of probability, and this would allow them to collaborate more efficiently to maximize the likelihood. Third, the probability of choosing each component regulates the collaboration and competition between the component models. It would allow some component models to respond more to the change, for example, of frequency of data point in the data. We also talk about the special case of fixing one component to a background word distribution, right? And this distribution can be estimated by using a collection of documents, a large collection of English documents, by using just one distribution, and then we'll just have normalized frequencies of terms to give us the probabilities of all these words. Now, when we use such a specialized mixture model, we show that we can effectively get rid of background words in the other component, and that would make the discovered topic more discriminative. This is also an example of imposing a prior on the model parameters, and the prior here basically means one model must be exactly the same as the background language model. And if you recall what we talked about in Bayesian estimation, and this prior would allow us to favor a model that's consistent with our prior. In fact, if it's not consistent, we're going to say the model is impossible, so it has a zero prior probability, and that effectively excludes such a scenario. This is also an issue that we'll talk more later.